What's the fundamental frequency? Excuse me?
Is it like
So if you're thinking of harmonic.
lowest frequency to create a wave, a standing wave?
Yeah, the lowest frequency to create a standing wave based on whatever links you're dealing with. So it's the lowest frequency that will create that standing wave. The harmonic, ma'am, that you were talking about is basically a multiple of that fundamental. The N? Where the N is basically your harmonic number. Okay? Or in this, on a string wave, that N would be the antinodes. Okay? All right. So kind of keep that in mind about the fundamentals and the harmonics, and we're going to go to the next page. And now we're going to be talking about open pipes. So first off, taking a look, if this right here is our pipe, okay, this is an open, well yes, it's closed pipes, open on one end. Closed pipes are open on one end, closed on the other. If this is our pipe, at the open end of that, is that an antinode or a node?
It's an antinode.
You are correct. And how do we know it's an antinode? Yep, it's our maximum energy. And that means if we're looking at that on the closed end of the pipe, what must it be to be a standing wave? It's going to have to be right here. That makes it a node. Okay, so you have to have that. Now, what we're going to do is we're going to say we have this graphic, and we're going to pretend that we have a pipe that's closed to one end, and this is our fundamental. Okay? This fundamental, the pipe is a length L. Okay? Pipe is a length L. First off, we're going to draw that same length L pipe around everything. So just do that really quick. All right, we got that part in there. Now, keeping in mind what we know about antinodes and nodes. Antinodes are our maximum energy, right? And nodes are our minimum energy. Which of these 5 harmonics are actually going to, which harmonics are actually going to happen? Which are going to be produced? Are they all going to be produced? Or is only a portion of them going to be produced? Take a look. Think about what you wrote, answer to number 1 and number 2. Which of these scenarios are actually going to produce harmonics?
All the odd number ones.
Why all the odd number ones?
Because when the cup opens, it's at the node with the max energy near the sound.
Right. Okay, think about it this way. Think about right here, this is our max energy so that we can hear this, right? If right here is the part that's being spread out, there's no energy there, right? So if there's no energy, there's no sound. Does that make sense? Okay. So then which harmonics can be produced in the pipe? Only the odd ones. Okay, so in a closed pipe, only the odd ones can produce the sound. Okay? So then for a pipe that is closed on one end, the sequence would be 1, 3, 5, plus, and then keep going on, however you want. Okay? So now let's talk about, we're going to start talking about our wavelength in terms of the L that we're given. Okay? Now, I'm going to, basically what we're doing here picture-wise is we're picking up this vertical one, right? And we're going to turn it sideways so we can see it, we can see the entire thing. Okay? So now from looking at that, let's go number 26. Okay? All right, first off, remember that 2 antinodes equal 1 wavelength. We did that on the waves on a string. We're correct? You need to have 2 of them? Okay. Yeah. Each antinode is one's an up, one's a down. So if we're looking at this picture here, how much of a wavelength is actually in the length of the pipe?
Half.
Nope. Look at the length of the pipe. Look at your diagram on the right. That's exactly, only 1/4 of that wave is in there, isn't it? Okay. All right, so what do we got here? So that means we have 1/4 of a wave. All right. We have 2/4 of a wave. We have 3/4 of a wave is in there. 4/4. And 5/4. So these portions of a quarter is the amount of wave that is inside the pipe. Okay? All right, that's what that is representing. The number on top is basically the portion of each wave that is in the pipe is based on a quarter. And we know that because of our fundamental frequency, in which only a quarter of our fundamental frequency is actually in the pipe. So that's where we're getting that 4 from, a quarter. Okay? So if 1/4 of a wavelength is L, how many lengths make up each wavelength? 4L, at least for talking about fundamental, right? All right. So that means here, I'm going to erase a little bit here, excuse me. That means right here, we've got 4L going to give us 1 wavelength. All right? We've got 4L over 1. Okay? And our next one, in the 4 parts of a wave that are needed for a length, 2 of them are showing up in the pipe. And the next one, if 4 lengths is 1 wavelength, 3 of those parts are showing up in there. And this one, 4 parts of a wave are showing up in the pipe. And now 5 parts of a wave. Did I get it backwards? Oh, I did it backwards up top. I'm sorry, not on the bottom. Thank you for catching that backwards. This should be 4/5, shouldn't it? Is that right? Nope.
No, it's the bottom.
Oh, so you are. I'm sorry, I got myself confused there. Thank you for catching me. We fix this bottom one, so it's 4L over 5. Is this starting to look a little bit familiar? Yeah, I know, right? Okay, so we've done 28. So do we see kind of what the pattern is going to be? What's the part that stays the same in this pattern we're seeing on the bottom? Okay, the wavelength is going to be equal to that. Okay, what's it going to be? The wavelength of a closed pipe.
4L.
4L over, and we're going to divide that 4 lengths into however many parts of a wave fit into the pipe. I'm sorry, not 2, I wrote it down. In. Where in is our harmonic. All right, because what, 1, 2, 3, 4, 5? There's our harmonic. So 4 lengths divided by n, the number of harmonics, tells you what is the wavelength that is inside of a closed pipe. All right. Okay, but that's our equation, but we know that for a closed pipe, only certain wavelengths are possible. Which are they? All right, odds. Do me a favor. I want you to take a few minutes. We'll calculate number 32, the wavelength of the third harmonic in the 60 centimeter long closed pipe. What do you guys end up getting as the wavelength of the third harmonic? 0.8, because we're going to do 4 times our length of pipe, which is 0.6. Divided by our number of harmonic is 3. So it's 2.4 divided by 3 is equal to I kind of ran out of room. 0.8. And what I want you to realize as well is what practical application of this. Who plays in band? 1, 2, 3. Or used to play in band or something. All right. Okay. What about who plays, say, woodwinds or some of woodwinds and brass? All right. You want to know what the storyboard is for? Okay. It's a very poor representation of a flute. Okay. Okay. Or it could be a clarinet. I want you to think, if you're playing, basically these are just a bunch of holes on here, right? Making this and it's essentially an open pipe. And so when I start pressing different keys, I'm changing the frequency, I'm changing the height, which in turn is going to change our wavelength, which is going to change our frequencies. All right, so that's how your instruments work. Okay. Now our stringed instruments work with the wave on a string, right? These ones are working as standing closed pipes. Okay. All right. So we're going to keep moving on from here, try and get through as much as we can. So that's harmonics in closed pipes. Now let's talk about harmonics in open pipes. That's our next bit. Okay. Whoops. Get this up a bit. Okay. So harmonics in open pipes. So first off, we got to remember, for it to be in a pipe and for it to actually create a harmonic which we can hear, what part of the wave has to be at the end of the pipe? Antinodes, because otherwise we can't hear it. We just can't hear it. So this is antinodes. All right. Antinode. So just keep in mind that in order for a pipe to make that sound, it must have, all right, it's got to have a standing wave. And for it to be a standing wave, you have to have at least one node and one antinode. All right, we kind of saw that on the closed pipe, right? Because there was one node in the bottom and one antinode at the top. When you're looking at this, how many antinodes are we seeing?
Two.
Two. Okay. So for each successive harmonic, the number of antinodes goes up by one. Take a look at your front page. By one. The number of antinodes. All right? That's your first, second, third, fourth, and fifth, right? If you're looking at that, notice that you're looking at the number of antinodes, right? So the number of antinodes goes up by one. So looking at that as well, starting from I guess the nodes, how does the number of nodes change as you go up for the harmonics? We can't really have half a node. Look at the picture. How many nodes are increased every time you go up a harmonic? Goes up by one, right? The first one has two nodes, and then 3, 4, 5, right? Okay, so it goes up by one. We're going to see something a little bit different in here, okay? Now, we have 4 pipes at the left. What we're going to do is we're going to draw the first harmonics, and we're going to see, is this true for the open pipe? So for it to draw another harmonic, what else do I need to put in there? If it goes up by a node, right? So I have to put another node, and each node is basically like half a wave. Okay? The easiest way to do this, guys, is to do this. Is to just draw that little egg thing in the middle, and there we go. So I now have 2 nodes, right? Or rather, I've gone up by, I got 3 nodes in there now. Right, we're going to go up again. I now need to have 4 nodes. Okay. Which is basically just, it's 2 ups, 2 downs. And now I'm going to add one more node to this. So in the middle, I'm going to have 3. Okay, now take a look at this. On the string, we said to figure out our number of harmonics, we count the nodes. The antinodes. 1 antinode, first harmonic, 2 antinodes, second harmonic, etc. All right, so we're going to count our antinodes to figure out our harmonic. What do we count on an open pipe? What feature of the wave tells us the harmonic number? Oh, take a look. What would we be counting? If you know that this one up here is the first harmonic, right? That's our first harmonic right there. First, second, third, and fourth. So which feature of the wave is telling you first, second, third, and fourth? Is it still the antinodes? Now it's the nodes, isn't it? Okay, because here's 1 node, 2 nodes, 1, 2, 3 nodes, 1, 2, 3, 4 nodes. So now we're looking at nodes. Yes?
Never have calculated.
Okay. All right, so there's our notes. So in this case, taking a look at what we know about what needs to be at the end of a pipe, which of these are actually going to produce harmonics that we can hear?
All of them.
Why?
Because they all have an answer at the end.
They all have an antinote at the end, so in this case, we will hear all the harmonics. Okay? All right, so now let's figure out our sequencing here. Okay? The same way we've done this. So first,
412.5.
okay, give me a sec. I gotta do this part first. All right. Okay. All right. So to get one wave, first I want you to see that this right here, if I do this, watch this. So, yeah, copy and paste, right? So that's half of a wave, right? So in the pipe, all right, there would have to be 2 lengths of pipe to give us 1 wave, right? Okay. If we had 2 lengths of pipe,
So, like, it would be one length, because that is a full wave, like, if they're like 2 separate halves, 2 halves.
no, it's only,
Oh, it's a-
no, it's
It
only,
has to go.
yeah, because you kind of put them together. So the question is, in this one, we say how many halves of a wave. I pull this over here. Take a look at that, right? So in this one, there are 2 halves of a wave. Okay, and the other one, it pretty much say it's going to be 3 halves of a, 2L over 3. And 2 lengths. Yeah, you'd have 3 waves. And in this one, in 2 lengths, you'd have 4 waves. So on a string and on an open pipe, 2 lengths give you 1 wave. All right. On a closed pipe, how many lengths give you a full wave? 4. Right.
So it's
That's okay. End of the class. Right. That means that for an open pipe, we're doing the same thing as a string, 2 lengths over n. Now, what was the frequency? And
412.5.
all right, I'm gonna go look for the tuning fork. That's that. You guys solved the last problem. Okay, for this last open problem, it was to find the wavelength of the 3rd harmonic in an 80 centimeter long open pipe. So that means that wavelength will end up being 2 times 0.8 divided by 3. So it's 1.6 divided by 3, so it's going to be 5.5 something. 1.6 divided by 3, 0.533 meters. Okay. And that covers our information about waves, standing waves in closed pipes and standing waves in open pipes. Have a great weekend.